What if everything you know is not what it seems? Imagine for a moment that every memory you cherish, every person you love, and every sunrise you have ever witnessed is not part of a physical, tangible world. What if instead your entire reality is nothing more than an incredibly sophisticated digital illusion? This is not a line from a science fiction movie. It is a profound question that thinkers and scientists are seriously considering today. The idea that we might be living inside a computer simulation forces us to confront the very foundations of our existence. It challenges our most basic assumptions about what is real and what is merely programmed code, compelling us to look at our universe with a new sense of wonder and skepticism. This captivating concept, often called the simulation hypothesis, has a powerful grip on the human imagination. It taps into a deep-seated curiosity about our place in the cosmos. Are we the masters of our own destiny, or are we simply characters in a cosmic play, orchestrated by an unseen intelligence? The thought is both exhilarating and unsettling. It suggests that the laws of physics that govern our universe might be nothing more than the underlying algorithms of a massive computational system. Every experience, from the simple joy of a shared laugh to the complex grief of a loss, could be a series of calculated data points within a simulated reality, a world built of information rather than matter. The allure of this theory is undeniable. It offers a potential explanation for some of the universe's greatest mysteries. Phenomena that seem strange or counterintuitive, such as the bizarre rules of quantum mechanics, could be seen as features of a simulated environment, much like the programmed physics in a video game. This framework invites us to become cosmic detectives searching for glitches in the matrix or clues left behind by the programmers. It transforms the study of the universe into a quest to understand not just the how of existence, but the why and who behind it all. The simulation hypothesis pushes the boundaries of human thought, demanding that we question everything we take for granted about the world around us. As we stand on the precipice of our own technological revolution, creating ever more realistic virtual worlds, the question becomes increasingly relevant. Is it possible that another civilization, far more advanced than our own, has already achieved this feat? Have they created countless simulations, each populated with conscious beings who believe their world is the one true reality? The implications are staggering, forcing us to reevaluate our significance in the grand scheme of things. Exploring this idea is not just a mental exercise, it is a journey to the heart of what it means to be conscious, to be human, and to exist in a universe that might be far stranger than we have ever dared to imagine. The question of our reality's nature is not a new one. It has echoed through the halls of philosophy for centuries, long before the first computer was ever conceived. Ancient thinkers grappled with the distinction between perception and reality. They wondered if the world we experience through our senses is a true representation of what is actually there. This timeless inquiry forms the philosophical bedrock upon which the modern simulation hypothesis is built. It demonstrates a long-standing human tradition of looking beyond the surface of our experiences, driven by an unyielding desire to understand the ultimate truth of our existence. This deep-rooted skepticism about the perceived world has paved the way for today's more technologically informed discussions. Today, this age-old philosophical puzzle has found a new home in the world of science. What was once confined to thought experiments and abstract debates is now being seriously considered by physicists, computer scientists, and cosmologists. The rapid and relentless advancement of our own technology has been the primary catalyst for this shift. We are developing artificial intelligence that can learn and adapt, and creating virtual realities so immersive they can fool the human brain. As we get better at simulating worlds, the possibility that our own world is a simulation becomes less of a fantasy and more of a logical extrapolation. The line between abstract speculation and testable scientific theory is beginning to blur in fascinating ways. The simulation hypothesis has transitioned from a fringe idea into a topic of serious academic discourse. It is discussed at prestigious scientific conferences and published in peer-reviewed journals. This evolution highlights a significant change in how we approach fundamental questions about the cosmos. Science is no longer just about measuring the physical world, it is also about exploring the nature of information, consciousness, and reality itself. The hypothesis compels us to ask whether the universe is fundamentally made of matter and energy, or if it is composed of information, with physical laws being the output of a cosmic computation. This brings philosophy and physics together in a powerful and exciting intellectual partnership. But is there any genuine scientific merit behind this mind-bending idea, or is it destined to remain a compelling but untestable thought experiment? This is the central challenge that researchers are now tackling. They are actively searching for ways to find evidence, to test the hypothesis, and to move it from the realm of possibility to the realm of scientific fact or fiction. The quest to determine whether we are living in a simulation is not merely an intellectual curiosity. It represents one of the most ambitious scientific endeavors imaginable, a quest to uncover the true fabric of our reality, and, in doing so, to fundamentally redefine our understanding of the universe and our place within it. The seeds of the simulation hypothesis were planted long before the digital age in the fertile ground of ancient philosophy. Thousands of years ago, the Greek philosopher Plato presented a powerful thought experiment known as the allegory of the cave. He imagined a group of prisoners chained inside a cave facing a blank wall their entire lives. Behind them a fire burns and puppeteers cast shadows of various objects onto the wall. For the prisoners, these flickering shadows are their only reality. They name them, study them, and believe them to be the true forms of existence, completely unaware of the richer, more complex world just beyond their perception. This ancient story serves as a profound metaphor for questioning the reality presented to us through our limited senses. Plato's allegory forces us to confront a deeply unsettling possibility that what we perceive as the real world might be a mere projection of a higher, truer reality that we cannot directly access. The prisoners in the cave are not wrong in their observations. Their world of shadows follows consistent rules, yet their understanding is fundamentally incomplete and illusory. This is the philosophical heart of simulation theory. It suggests that we, like the prisoners, might be observing a reality that is perfectly consistent and logical within its own framework, but is ultimately a simplified representation of something far more fundamental. This timeless idea encourages a healthy skepticism about the evidence of our senses and pushes us to consider what might lie beyond the veil of perception. Centuries later, in the 17th century, the French philosopher René Descartes took this skepticism to a new level. In his Meditations on First Philosophy, Descartes embarked on a quest for absolute certainty, systematically doubting everything he believed to be true. He considered the possibility that his senses were deceiving him, that he might be dreaming, or even that an all-powerful malicious demon was systematically feeding him a false reality. This evil demon hypothesis is a direct philosophical precursor to the modern simulation argument. Descartes imagined a deceptive entity capable of creating a complete illusion of an external world, including his own body, and all his sensory experiences, making it impossible for him to distinguish truth from fabrication. Descartes' radical doubt led him to his famous conclusion, cogito, ergo sum, I think therefore I am. He reasoned that even if an evil demon was deceiving him about everything else, the very act of being deceived, of thinking and doubting, proved his own existence as a thinking being. This insight is crucial because it separates the existence of consciousness from the reality of the external world. It opens the door to the idea that a mind can exist independently of a physical, base reality. This separation is a cornerstone of the simulation hypothesis, which posits that our consciousness could be a product of a computational process existing within a simulated universe independent of any traditional physical substrate. While ancient philosophy laid the conceptual groundwork, it was a 2003 paper by Oxford philosopher Nick Bostrom that propelled the simulation hypothesis into the realm of serious, modern academic debate. Titled, "Are You Living in a Computer Simulation?" Bostrom's work shifted the conversation from a purely metaphysical question to one grounded in probability and logical reasoning. He did not claim that we are definitively in a simulation. Instead, he presented a powerful argument in the form of a trilemma, suggesting that one of three very specific and mind-bending propositions must almost certainly be true. This framework provided a new rigorous way to approach the problem, sparking a wave of discussion among scientists and philosophers alike. Bostrom's trilemma is built on a few reasonable assumptions about the future trajectory of technologically advanced civilizations. The first proposition is that the fraction of human-level civilizations that reach a post-human stage, a stage of technological maturity capable of running high-fidelity ancestor simulations, is close to zero. This would mean that civilizations like ours almost always go extinct before they can develop such powerful computing. They might be wiped out by war, pandemics, asteroid impacts, or self-inflicted technological disasters. If this is true, then simulations are rare simply because the simulators themselves never come to exist, and we are likely living in the base physical reality. The second proposition of the trilemma suggests that nearly all post-human civilizations lose interest in running ancestor simulations. Perhaps they are bound by ethical constraints that forbid simulating conscious beings, or maybe they simply have other priorities and find such projects boring or pointless. If advanced civilizations have the capability but universally choose not to run simulations of their evolutionary past, then the number of simulated minds in the universe would be negligible. In this scenario, despite the technological feasibility, we would again have to conclude that we are almost certainly members of the original, non-simulated civilization, as very few simulations would exist. The third and most startling proposition is that we are almost certainly living in a computer simulation. This conclusion follows logically if the first two propositions are false. If a significant number of civilizations do survive to reach a post-human stage, and if even a small fraction of them decide to run ancestor simulations, the sheer number of simulated realities would be astronomical. A single advanced civilization could run billions of simulations, each containing trillions of simulated conscious beings. Consequently, the number of simulated minds would vastly outnumber the real organic minds. If this is the case, then from a purely statistical standpoint, it is overwhelmingly more probable that we are one of these simulated minds rather than one of the original simulators. For the simulation hypothesis to be, scientifically plausible, one fundamental idea really has to hold true: the principle of substrate independence. This concept suggests that consciousness is not tied to any specific biological material. In other words, a thinking, feeling mind doesn't necessarily require a brain made of neurons and organic tissue. Instead, consciousness could actually be a process, a complex pattern of information processing that can be realized on any sufficiently powerful computational system. This idea is a critical bridge connecting philosophy with computer science. It opens the door to the notion that we could be uploads, running on hardware we can't even imagine yet. Think of it like software on a computer. The same application can run on different types of hardware. It can run on a laptop, a desktop, or even a smartphone. The underlying physical material is different in each case, but the software's function remains fundamentally the same. Substrate independence applies this same logic to consciousness itself. If our minds are essentially sophisticated software, then the hardware they run on could be something other than biology. It could be silicon-based or based on exotic computation developed by advanced civilizations. This principle isn't just a wild guess. It's rooted in the computational theory of mind, a major branch of cognitive science. This theory says the human mind operates like a biological computer, processing information to produce thoughts, emotions, and behaviors. If this is correct, we could replicate these processes on non-biological machines. We're already taking first steps with artificial intelligence and neural networks designed to mimic the brain's structure. As these technologies advance, they show that intelligent processes aren't exclusive to biological life, making simulated consciousness seem less like fiction. Therefore, the possibility that our entire universe operates as a vast computational network becomes a serious consideration. Our feelings of love, our sense of self, and our perception of the world could all be the result of complex calculations executed moment by moment. The physical world we interact with might be the graphical interface of this cosmic computer, rendered for our benefit. Substrate independence is the key that unlocks this possibility, suggesting consciousness is a universal property of complex information processing, a program that can run on any platform powerful enough, including the one hosting our potential simulation. If our universe is a simulation, its foundation is information, not matter or energy. Some physicists, like Melvin Bostrom, propose that the universe optimizes and compresses information, much like a computer. Bostrom second law of infodynamics suggests information in an isolated system tends to decrease or stay constant, challenging the traditional view that disorder always increases. This mirrors how digital files are compressed, redundancy is eliminated, and only essential data remains. If proven, this principle would be strong evidence for a computational universe, where reality is built from bits of information. The laws of physics could be seen as algorithms processing these bits, echoing John Archibald Wheeler's "it from bit" philosophy. Our universe, then, is not a physical place but the output of a cosmic computation. This perspective allows us to make testable predictions. If the universe compresses information, we should find evidence of it. Vopson has even proposed experiments to measure the information content of particles. Discovering that the universe prioritizes information efficiency would be a major clue that we're living in a programmed reality. Quantum mechanics offers some of the most intriguing hints for the simulation hypothesis. At the quantum level, particles exist in superposition and can be entangled across vast distances, behaviors that defy classical logic. But if reality is a simulation, these quirks could be programming shortcuts to save resources. In quantum theory, a particle's state isn't definite until observed, much like a video game only renders what the player sees. This observer effect suggests the universe computes outcomes only when measured, optimizing processing power. The existence of Planck units, the smallest possible measurements, could be the universe's pixel resolution. The speed of light as a universal limit might reflect the maximum processing speed of the underlying hardware. These features aren't proof, but they hint at a reality that's computed, not continuous. The weirdness of quantum mechanics may be the signature of a simulated world. Each observation could be the universe rendering reality in real time. The simulation hypothesis reframes quantum strangeness as evidence of clever cosmic programming. The simulation hypothesis gains credibility as our own technology advances. Elon Musk and others argue that as simulations become more realistic, it's likely we'll create worlds indistinguishable from reality. Our progress, from Pong to photorealistic games, shows exponential improvement. If future civilizations can run countless such simulations, the odds favor us living in one now. Moore's law and emerging technologies like quantum computing suggest we'll soon have the power to simulate entire universes. The idea isn't just about games, it's about the exponential growth of computing itself. Unless all civilizations self-destruct or choose not to simulate, simulated realities could vastly outnumber base realities. Our ability to create virtual worlds is strong circumstantial evidence for the hypothesis. We're on the verge of becoming creators ourselves, making it plausible that we're already creations. The simulation hypothesis is no longer just science fiction, it's a logical extension of technological progress. The simulation hypothesis challenges our deepest ideas about reality and illusion. If a simulated world is perfectly consistent and conscious beings experience it, is it any less real? Philosopher David Chalmers argues that virtual reality is genuine reality for its inhabitants. The experiences, emotions, and interactions within a simulation are real to those who live them. Consciousness may be substrate independent, whether biological or digital. Real pain and joy are still felt. Dismissing simulated experiences as fake is a bias toward our own biology. Chalmers suggests we see simulated worlds as valid realities, not mere illusions. This perspective shifts our focus. The meaning of life isn't about being in base reality, but about the quality of our experiences. Our relationships, choices, and awareness are real regardless of the universe's underlying nature. The simulation hypothesis invites us to appreciate the complexity and significance of our world, whatever its origin. If our lives are part of a simulation, what does that mean for purpose and meaning? Some fear it implies we're just following a script, but many philosophers argue meaning is something we create. Whether our universe is random or designed, we still make choices, form relationships, and seek growth. The love we feel and the knowledge we pursue are real, regardless of the substrate. A creator or programmer could even add new dimensions of purpose. Perhaps we're part of a cosmic experiment or story. The simulation hypothesis doesn't strip life of meaning, it deepens the questions we ask. What matters is how we live within our reality, not who or what created it. The search for meaning is a journey we define for ourselves. Our purpose is what we make it, simulation or not. While the simulation hypothesis presents a compelling narrative, it faces significant challenges from the scientific community. A primary objection revolves around the sheer complexity and the apparent inefficiency of our universe. Physicists like Nobel laureate Frank Wilczek argue that if our reality were a simulation, it would likely be designed with elegance and computational economy in mind. An advanced civilization possessing the power to simulate an entire cosmos would surely program it efficiently. Yet when we examine the laws of physics, we find they are often messy, redundant, and far more complicated than they need to be. This hidden complexity suggests a natural, rather than an artificial, origin. Wilczek points out that the fundamental laws governing our universe are intricate and often counterintuitive, without any obvious purpose for their specific structure. Why would a programmer build a reality with so many seemingly arbitrary constants and layers of physical law? An intelligent designer would likely opt for simpler, more streamlined code. Instead, our universe appears to have what he calls superfluous complexity. It is filled with details and processes that seem to have no direct impact on our macroscopic reality. From this perspective, the universe does not look like a clean, optimized program, but more like a system that has evolved through natural, unguided processes over billions of years, with all the untidy baggage that entails. This argument is further strengthened when considering the computational resources required. A competing theory put forward by physicists Zohar Ringel and Dmitry Kovrizhin demonstrates a major roadblock for the simulation hypothesis. They prove that simulating certain quantum phenomena, specifically the quantum Hall effect, on a classical computer would require computational resources that grow exponentially with the number of particles involved. To simulate just a few hundred electrons would require a computer built from more atoms than exist in the entire observable universe. This suggests that simulating our reality, with its vast quantum complexity, is not just difficult, it may be fundamentally impossible within the known constraints of computation. Therefore, the argument from complexity presents a powerful counter-narrative. It proposes that the universe's messiness is actually a sign of its authenticity. An engineered reality would likely be stripped down to its essential components, optimized for performance like a well-designed piece of software. Our universe, however, appears to be the opposite. It is lavishly, almost wastefully complex. The immense computational power needed to capture every quantum quirk in physical law accurately seems to defy the very idea of an efficient simulation. These critiques suggest that if we are in a simulation, its creators were either remarkably inefficient or are operating with a form of logic that is entirely alien to our own. Beyond the challenges of complexity and computational cost, the simulation hypothesis faces a more fundamental philosophical objection. It may not be a scientific theory at all. A core principle of the scientific method is the concept of falsifiability, famously articulated by philosopher Karl Popper. For a hypothesis to be considered scientific, there must be some conceivable experiment or observation that could prove it false. If a theory can explain every possible outcome and can never be disproven, it moves from the realm of science into the realm of metaphysics or belief. Many critics, including physicist Sabine Hossenfelder, argue that the simulation hypothesis falls squarely into this unfalsifiable category. Hossenfelder asserts that the simulation argument is inherently unscientific because it can be endlessly adapted to fit any evidence we find. For example, if we discover that the universe is messy and inefficient, a proponent could simply argue that the simulators programmed it that way, perhaps to make it seem more real or for reasons beyond our comprehension. If we find evidence of a discrete pixelated spacetime, it supports the theory. But if we find that spacetime is perfectly smooth and continuous, one could argue that the simulation's resolution is just too high for us to detect. This ability to explain away any contradictory evidence makes the hypothesis impossible to test in a rigorous scientific manner. This lack of falsifiability places the simulation hypothesis in the same category as other untestable ideas, such as the existence of a non-intervening deity, or the idea that the universe was created 5 minutes ago with all our memories already in place. While these are interesting philosophical concepts to ponder, they lie outside the boundaries of what science can investigate. Any glitch in the matrix we might find could always be explained as an intended feature of the simulation. Any perfection we observe could be attributed to the skill of the programmers. Without a clear prediction that, if proven false, would invalidate the entire theory, it remains a compelling but ultimately speculative idea. This critique does not mean the simulation hypothesis is wrong, it simply means that it may be a question that science is, well, just incapable of answering. It becomes a matter of logic and probability, like Bostrom's trilemma, rather than empirical evidence. The theory can be a powerful tool for philosophical reflection and a source of creative inspiration, pushing us to question our assumptions about reality. However, until a concrete, testable, and falsifiable prediction is proposed, many scientists will continue to view it as an intriguing thought experiment, a modern technological version of Plato's cave or Descartes' evil demon, rather than a viable scientific model of our cosmos. Despite the profound challenges, the debate over the simulation hypothesis is far from over. A dedicated group of scientists believes the question is not purely philosophical and is actively pursuing ways to empirically test it. They're moving beyond thought experiments and actually designing real-world experiments to search for tangible evidence. Their approach is pretty straightforward. If our universe is a simulation, it must be running on some kind of computational hardware. This hardware, no matter how advanced, would probably have limitations that could show up as detectable artifacts within the simulation itself. The goal, then, is to hunt for the digital seams of our reality, the cosmic equivalent of pixels on a screen. One of the most prominent proposals comes from a team of physicists including Silas Bean, Zohre Davoudi, and Martin Savage. They suggest that a simulated reality would not be continuous but would instead be built upon a discrete, underlying grid or lattice, kind of like the grid of pixels that creates a digital image. While this grid would be incredibly fine, far smaller than any atom, its existence might have subtle, observable consequences on the most energetic particles in the universe. They propose that we could find evidence of this space-time lattice by studying the behavior of ultra-high-energy cosmic rays. These particles travel across the cosmos with immense energy, and their properties might be slightly altered by the grid-like structure of space. According to their theory, this underlying lattice would impose a fundamental limit on the energy a particle can have. Just as a character in a video game can't move between the pixels, a cosmic ray in a simulated universe might not be able to travel equally in all directions. The grid would create a slight directional preference or anisotropy in their distribution. If we were to observe that the highest energy cosmic rays do not arrive on Earth uniformly from all directions, but instead follow a specific pattern that aligns with a grid model, it would be a bombshell discovery. It would provide the first concrete experimental evidence that our reality is not the seamless, continuous fabric we perceive it to be. This search for cosmic pixels represents a bold and innovative approach to one of humanity's oldest questions. It transforms a metaphysical puzzle into a testable, scientific hypothesis. While the technical challenges are immense, the potential payoff is, well, revolutionary. Finding evidence of a discrete space-time would be a discovery on par with the revelations of Copernicus or Einstein, fundamentally reshaping our understanding of the cosmos. These experiments, whether they succeed or fail, push the boundaries of physics and cosmology, encouraging us to look at the universe not just as a physical space, but as a potential piece of immense and extraordinary technology waiting to be understood. While some scientists search for physical clues, others are exploring the quantum realm for evidence of computational efficiency. Physicist Thomas Campbell, for instance, has proposed experiments aimed at distinguishing between the predictions of standard quantum mechanics and those of a reality based on computational logic. The idea is to see if quantum behaviors align more closely with a system trying to save processing power. These experiments often involve testing the limits of quantum uncertainty or the nature of the observer effect. If quantum mechanics is indeed a set of shortcuts for a resource-limited simulation, carefully designed experiments might be able to catch the system in the act of optimizing, revealing its computational nature. However, the very act of searching for proof that we live in a simulation raises a chilling and profound paradox. Philosopher Preston Green at Nanyang Technological University has raised a serious ethical concern about this entire endeavor. He suggests that proving our reality is a simulation could be an existential threat. If we are part of an experiment or a simulation being run by a higher intelligence, what would happen if the subjects, us, discovered the truth? Green argues that our creators might have a vested interest in keeping the simulation's nature a secret. Our discovery could be seen as a sign that the experiment is contaminated or has reached its conclusion. This leads to what could be called the observer's paradox of simulation theory. If we find conclusive evidence that we are in a simulation, the simulators might simply decide to shut it down. The very act of confirming the hypothesis could trigger our annihilation. This presents a terrifying dilemma for scientists. Is the pursuit of this ultimate truth worth the risk of erasing our entire existence? It is a high-stakes gamble where the discovery itself could be the cause of our demise. This idea suggests that perhaps the reason we have not found any evidence yet is that any civilization within a simulation that gets too close to the truth is promptly deleted. This potential risk adds a layer of immense gravity to the scientific search. It's no longer just a quest for knowledge, but a decision with potentially catastrophic consequences. The evolving fields of artificial intelligence and virtual reality continue to propel these discussions forward, making the line between our reality and a simulated one seem thinner every day. As we build our own digital worlds and populate them with increasingly sophisticated AI, we are forced to confront the ethical implications of our own potential creations. This, in turn, makes us reflect on our own situation, leaving us to wonder if we should continue pulling at the thread that might unravel everything. Ultimately, the simulation hypothesis may be a question that we are never able to definitively answer. The evidence may remain forever elusive, and the critiques of unfalsifiability might hold true, leaving the theory suspended in the fascinating space between science and philosophy. Yet the true power of this idea does not necessarily lie in finding a final, concrete answer. Its value is found in the very act of asking the question. To seriously contemplate that our reality might be a simulation is to engage in one of the most profound intellectual exercises possible. It forces us to step outside our ingrained assumptions and view our universe, our lives, and our consciousness through a new and transformative lens, sparking a sense of wonder that is the very engine of scientific discovery. This grand inquiry compels us to reconsider the fundamental nature of existence itself. Is the universe a collection of matter and energy, or is it fundamentally composed of information? Is consciousness a rare biological fluke, or is it a universal property of complex computational systems? These are the questions that the simulation hypothesis brings to the forefront of modern thought. It serves as a powerful catalyst for interdisciplinary exploration, uniting physicists, computer scientists, philosophers, and theologians in a shared quest to understand our place in the cosmos. The hypothesis is a tool for thought, a framework that encourages us to push the boundaries of knowledge and imagination, regardless of whether the framework itself turns out to be true. The journey of exploring this concept has already yielded incredible insights. It has pushed physicists to look for new ways to test the fabric of space-time, and has given philosophers new language to discuss the nature of reality and experience. It has forced us to confront the ethical implications of our own rapidly advancing technology, particularly in the fields of artificial intelligence and virtual reality. As we stand on the cusp of creating our own simulated worlds populated with conscious AI, the questions raised by the simulation hypothesis become less abstract and more urgent. The theory acts as a mirror, reflecting our own creative and potentially destructive capabilities back at us. Whether our universe is a base reality or one of many simulated descendants, the act of questioning its foundation is an essential part of the human, or conscious experience. It is born from our innate curiosity, our desire to look beyond the horizon and understand what lies behind the curtain. The simulation hypothesis is the latest chapter in this timeless human story, a modern myth that encapsulates our hopes and fears about technology, existence, and the unknown. Its enduring power lies not in providing an answer, but in its ability to inspire us to ask deeper, more challenging questions about the world we inhabit and the nature of our own minds. In the end, we're left to wonder if the ultimate nature of our reality truly changes the significance of our lives. If we were to discover tomorrow with absolute certainty that we are living inside a computer simulation, what would change? The sun would still rise, we would still feel the warmth of a loved one's embrace, and we would still be faced with the daily challenges and joys that define our existence. The pain of loss and the thrill of discovery would be no less potent. The reality we experience is the only one we have, and its contents are what give our lives substance. The search for meaning has always been an internal journey, a process of creating value through our actions, relationships, and aspirations. The profound experiences that constitute a human life, love, empathy, creativity, and the quest for knowledge, retain their value regardless of the substrate they are running on. A symphony does not become less beautiful because it is played on a digital device instead of a vinyl record. Similarly, a life filled with purpose and connection is not devalued if its backdrop is informational rather than physical. The meaning we find in our lives is emergent, arising from the complex interplay of our conscious experiences. It is something we build together, within the rules of our given reality. The simulation hypothesis does not erase this meaning, it simply reframes the stage on which our stories unfold. Perhaps the most important takeaway from this entire exploration is a renewed sense of humility and awe. Contemplating the simulation hypothesis encourages us to appreciate the immense, almost incomprehensible complexity of our universe. It reminds us that our current understanding of reality is likely incomplete, just as the understanding of those who came before us was. Whether our world was born from a Big Bang or booted up by a cosmic programmer, we are participants in something truly magnificent. This perspective can foster a deeper connection to the cosmos and to each other, as fellow travelers in this mysterious and beautiful existence, trying to make sense of it all. Ultimately, the significance of our lives is not written in the code of the universe, but in the choices we make every day. It is found in our capacity for kindness, our courage in the face of adversity, and our unyielding curiosity that drives us to ask these very questions. The love we share, the art we create, and the knowledge we pass on to future generations are all profoundly meaningful, regardless of the ultimate architecture of reality. Our experiences are real to us, and in the end, that is what truly matters. Our purpose is not to be found in the origin story of the cosmos, but in the living of our lives, here and now.